All right, good afternoon, everyone. This video is for 10.7 notes, but today is Logan Family Friday on our chill week. So we're going to start by getting our quizzes back, and then we're going to go to our notes. So in addition to your notes, you also need to grab your perfect card, okay? So if you're watching this on the video, you should pause it and grab your perfects card, right? That's the big yellow sheet that I gave you that has all the stuff like 1 squared equals 1, or 2 squared equals 4, and then they also have the part that says like the square root of 25 equals 5, that kind of stuff, back and forth, okay? All right, so I'm gonna jump into the notes for the video here. And we are on 10.7 notes, and we are still doing what we've been doing, which is factoring, okay? We've been doing a lot of smiley face factoring, okay? And we've also been doing some factoring with GCF, greatest common factor. So all those words go together. Today we're going to look at some special ones that come up. And this first type, this first page, is very common. And if we recognize this pattern, it's really easy. And that's the hope, that we recognize the pattern that's coming up here. Okay? But remember, a lot of things in math are opposites. And so factoring is actually opposite of foiling. And we know what foiling means. When I FOIL, it looks like this. It's that first, outside, inside, last. And so we're going to actually try to discover this pattern by starting with foiling. So when I look at number 1 here, and it says multiply these, I certainly am going to FOIL this. So I want you to notice as well that these two things look very similar, right? That is an m minus 3, and that is an m plus 3. So those are really similar. The only thing that's different is the plus and the minus. And so when we FOIL this, okay, let's see what actually happens. I'm going to first take m times m, which is m squared, m times positive 3, which is positive 3m. When I go to the inside, that's a negative 3 times m, which is negative 3m. And negative 3 times a positive 3 is negative 9. Now, what do you notice? These two things are like terms, and not only are they like terms, but they are opposites, okay? And those opposites cancel each other out, and therefore the answer to this is m squared minus 9. Interesting. Do you notice any connection between what I started with and what I ended with? Do you notice that m squared is really that m, the first term, squared? And do you notice that 9 is my last term squared? That is interesting, isn't it? I wonder if that happens all the time. Let's find out. Let's look at number 2. In number 2, we're going to FOIL this out again. And again, I want you to notice something. These two binomials look very, very similar. I have a 5y plus 6, and I have a 5y minus 6. So I have the same first term and the same last term for both of those. And if I FOIL that, like we did before, 5y times 5y for first is going to give me 25y squared. 5y times negative 6 is a negative 30y. Inside, positive 6 times 5y is going to give me a positive 30y. And a positive 6 times a negative 6 gives me a negative 36. What happens here? The exact same thing. Those middle terms are identical, but they're opposite, so they cancel out, and that leaves me with a 25y squared minus 36. And just like the last time, to get this 25y squared, really, I'm just taking that first term, 5y times 5y, I'm squaring that, and to get this 36, I'm taking that 6 times 6 and squaring that. And so that pattern continues. So this is what I'm talking about. This is my special pattern. The pattern is called a difference of squares. And I will oftentimes just write that as DOS, difference of squares. And really, what we're doing here is we're going backwards in our factoring. So we're actually would be starting here and ending right there. So we're unfoiling these for factoring, all right? Now, we know what these are because the first term we had to get by squaring something. We have that w squared. How do I get that? I take w times w. And to get that last term, 100, 100 is also a perfect square. If you look at your card, the square root of 100 is 10, or I could say 10 times 10 is 100. So when I start with this right here, it is a difference of squares. It means that my two terms are perfect squares. They're on my card, and they're separated by this minus sign, right? That's a difference. The word difference in math means minus or subtract. If I start with a difference of two squares, I can automatically tell you what the answer is. The answer is the terms in these parentheses are the square roots of the terms in the problem. So I'm thinking backwards. I'm saying the square root of w squared is w, and the square root of 100 is 10. And in my answer, which, by the way, that's my answer this time, that means I will always have a plus sign and I will always have a minus sign. This is kind of just a formula. It's almost like a recipe. So I don't have to care about positive and negative numbers. I just have to care about the plus and the minus. Okay? So if I recognize that pattern, factoring this stuff gets pretty easy. So it says factor each binomial completely. Notice that says binomial, which means it's two terms instead of the three terms that we had to use for smiley face. It also says make sure you check for the characteristics. So what I'm looking for is, are these things perfect, right? Are they perfect squares? And is there a minus sign in between them? Now, we have talked for a long time about GCF. I still want to look for a GCF first. I don't care that there's only two terms, but I'm going to check for a GCF. So in number one, my first question is, do I have a GCF of h squared minus 121? No. Okay. So my next question becomes, are these numbers perfects? Is h squared a perfect square? It is. And the square root of h squared is h. Okay. Is 121 a perfect square? It is. On your card, the square root of 121 is 11. So by using this formula, right, I take those two perfect squares and I'm going to write them down, and I'm just going to separate them by a plus and a minus. So this answer should say h plus 11 times h minus 11. And I am finished. That's it. That's my answer. Okay, number two. Same question. Now, it looks weird. It looks more difficult because there's a fraction there. My first question still should be, is there a GCF? Do you think there's a GCF of w squared and then a number? No. Okay, so then my next question is, if it's two binomials like that, are they perfect squares? And are they being subtracted? So, is w squared a perfect square? Yep, because the square root of w squared is w. Is 4 over 25 a perfect square? It is, because that's the same as me saying the square root of 4 over the square root of 25. And so we know that is really 2 over 5. And so even though this looks more complicated, I'm just going to connect them the same way as I have been. So I'm going to say W plus that 2 over 5 times W minus that 2 over 5. And that's it, right? If I recognize the pattern, I'm good to go. All right, number 3. Now, number 3 is a little weird. There's some big numbers in there. So my first question, do we think there's a GCF between 49t squared and 100x squared? The answer should be no, because I don't have anything that goes into 49, and they don't share any of those variables. One's a t, one's an x. Okay, so my next question is then, are they perfects? Is 49t squared a perfect? It is. 49's on my card, right? Square root of 49t squared is actually 7t, because I would have to square the 7 and the t to get back the t squared. Okay, and I'm double checking. There is a minus in between here. That's important. And then, is 100x squared a perfect square? Yeah, because that would be 10x. Good, so that means I should be able to write this, right, as 2 things plus, 2 things minus. I just take those terms. So I'm gonna write 7t plus 10x and 7t minus 10x. And that is it. Good, hopefully this is making sense. This pattern is making sense. All right, number 4 looks a little different. Now, my first question should always be, is there a GCF? With 16y to the 4th and 81, I don't think so. The only thing I know that goes into 16 are things like 2 and 4 and 16, and none of that's going to go into 81 because it's odd. Okay, so there's no GCF. The next question is, are these things perfect? Perfect squares? Well, they actually are. 16y to the 4th is really 4y squared when I take the square root of that. And the square root of 81 is actually 9. Okay, but I have a problem here. Does anybody see what my problem is? My problem is right here. That is a plus sign. That is a sum, not a difference. So what does that mean? I can't factor this. This doesn't get any more factored because that's a plus sign. So when we said it has to follow all of our characteristics, we were being truthful. I have to have a minus in between all of those things in order to be able to factor. If I don't have that, I don't get to factor. Okay, let's see. Let's look at number 5. So knowing what we just said, some of you might be looking at number 5 and saying, well, hey, there's a plus sign there, so I must not be able to factor this. But there's something weird happening here as well. Would you all agree that this number is negative? And that really could mean plus a negative or subtract. And because I'm adding these 2 terms, those 2 numbers, I actually could switch them because the order in adding doesn't matter, right? If I said to you 3 plus 5 or 5 plus 3, I get the same answer. So I can always switch the order of numbers. So what if I did that? What if I said this is really 81 minus 25a squared? Now I have the minus sign that I need. Is 81 perfect? Does it have a square root? It sure does. That's 9. Is 25a squared perfect? Does it have a square root? It does. That would be 5, but not just 5, 5a. And therefore, because those things are perfects and I have a minus in there, I'm able to rewrite these, right? So this is going to be 9 plus 5a and 9 minus 5a. Good. Okay, let's take a look at number 6. Number 6 also is a little different. Like right away, I notice that 2 is not perfect, but m squared is perfect. Does anybody know what I'm missing here? There should be a GCF. What number goes into both 2m squared and 32? 2 does. And so just like we did earlier, I'm going to start by putting that 2 out in front, and I'm going to divide everything by 2. That leaves me with an m squared minus 16. Okay, so then that 2 is just going to come along for the ride, and then I'm going to check everything else. I'm going to say, are they being subtracted? Yes. Is the first term perfect? Yes, because the square root of m squared is m. Is the second term perfect? 16 is, square root of 16 is 4. So now, just like before, I leave the 2 out in front. And just like before, I'm going to have a plus and a minus. And I'm going to plug that in as m plus 4 and m minus 4. So I can't forget about my GCF, okay? Good. Now, that is all difference of squares, and that shows up quite a bit. But we have one more kind of problem here, and we're going to, again, start by multiplying polynomials. And so we're going to look at what actually happens. So when you see something that says x plus 5 quantity squared, what does that mean to do? It should mean to take x plus 5 times x plus 5. And what do I have to do then? FOIL it. Now, do you think that these things are going to cancel out like they did last time? I don't think so. Let's see what happens. This time, both of these terms have pluses in the middle. So when I FOIL, first gives me x squared. Outside is a positive 5x. Inside is another positive 5x. And last is 25. So now I still have like terms here, but those like terms double, right? This is x squared plus 10x plus 25. Interesting. So is there some sort of a pattern from my answer to what I started with? I think so. I see that if I start with this x, that becomes x squared. I know that if I take the 5 times x, that middle term, and I multiply it by 2, there's 2 of them there, so that gives me a 10x. And if I go to that last term and I square it, I get 25. So this is actually a shortcut, okay? So let's see what happens when I do this again. So on number 2, the biggest difference I notice is that this says minus. They're obviously different numbers, but if I square this, I'm writing 2y minus 3 times 2y minus 3 again. And I'm going to FOIL that again. So first would be that 4y squared. Outside is a negative 3y. Inside's another negative 3y, so we're doubling up that middle term. And last would be positive 9 in this case. So again, those are like terms, and we're going to combine everything. So this gives me 4y squared minus 6y plus 9. And again, there is a connection here. That 2y, when I square 2y, I get 4y squared. When I multiply those two things together, that gives me a 6y. Oh, did I screw this up? 2y times. You guys, and nobody was here to tell me. I'm sorry. This should be a negative 6y each time. 2 times 3 is 6, not 3. Which means that this is a 12y, negative 12y. I apologize for that. Which then fits my schedule that that's 2 times the 6y. The only thing that's different is that's a negative. So when I have a minus in there, it makes it negative. And then the last term, that 3, I square that 3. And so this actually is another pattern. And these patterns are called perfect square trinomials. Okay, so trinomial means 3 terms. Perfect square shows up in here again. And I like to call these PSTs. And sometimes I pronounce it like psst, like I'm whispering to you. Like, hey, psst, do you notice anything here? It's a PST, it's a shortcut. And when I'm looking at that, so the characteristics of this shortcut are that my first and my third terms are perfect squares. I can find those on my card. So in this particular case, x squared is perfect, 49 is perfect. The second term, or the middle term here, is always going to be 2 times the product of the square roots of those other terms. So I kept saying it was double, right? Double the 5x, double the 6y. That's the same as me saying 2 times that middle term. So when I take this square root, right, it's like taking 2 times the square root of the first term and the square root of the last term, which is 2 times x times 7 in this case. And if that works, it's like a check. It's like, does it fit the pattern? If it does, then I know my answer automatically. I know that the terms in the parentheses are the square roots of the terms in the problem. And that the answer is always a binomial squared. It's always taken to that second power. Now, the sign, when I say the sign, I'm talking about plus or minus. And that sign is going to be determined by the first plus or minus sign. And I mean that to be way up here. Since that says plus, I will have a plus in my answer. When I did these problems back here, there was a plus there, there was a minus there, which changes the sign of my middle terms. Okay? Sometimes these are harder to recognize, okay? And so we're going to kind of go through it. And again, these are 3 terms. And P.S., it always works to smiley face this stuff too if this isn't making sense to you, okay? But I think we should try it for right now. So if I'm going to check for my characteristics, I'm always, again, going to start by looking for a GCF. But if I don't have one, or even if I do, I'm going to check my next characteristics. So for number 1, m squared, 10m, 25. GCF? No. If there's not a GCF, then I'm going to ask, okay, is my first term a perfect square? Yeah, it's m, right? Square root of m squared is m. Is my last term a perfect square? It is. It's 5. Okay, so far so good. So then the check is it 2 times those 2 numbers to get me my middle term? The answer is yes. 2 times m times 5 makes 10m. Therefore, this is a perfect square trinomial. So I can use my shortcut. So the shortcut simply says this. I put the m down. I choose this sign, so that's a plus. And then I put the 5 down. And then I close it up and square it, and I'm done. That's it. All right. What about number 2? Again, I'm going to start by asking, is there a GCF? What do you guys think? Nope, no GCF. So then I'm going to check my first and last term. Is my first term perfect square? Yep, square root of w squared is w. Is my last term a perfect square? Yep, square root of 121 is 11. And then I check my middle term. Is 2 times w times 11 equal to that middle term? Sure is, which means that I can rewrite this right away. So I take the first one, w. This time there's a minus, so I make it minus. I take the last one, 11, and then I square it. And I'm done. That's how it factors. Good. Okay. Number 3. Ooh, those look like big numbers. So my first guess is maybe there's a GCF. Let's see, 16, 40, and 25. Ooh, that 25 doesn't look very good. So 16 doesn't go into any of those other numbers. I don't think there's a GCF here. Okay, well, then let's go to our terms. Is my first term a perfect square? Yes, it is. Square root of 16y squared is 4y. Okay, is my last term a perfect square? 25w squared is 5w. Okay, then I need to check my middle term. So this is weird because it's got w's and y's, but that's okay. So my question is 2 times 4y times 5w going to equal that middle term? 2 times 4 is 8, times 5 is 40, and I have a y and a w. Looks like it is. Good. So that means I can use my shortcut, and I start with the first term. What do you think that would be? If you said 4y, you would be right. Do I put a plus or a minus down in the middle? If you said minus, you would be right because I take whatever that term is, whatever that sign is. What do I put down next? If you said 5w, you would be right because I just take whatever that is, and then I close it up and square it, and I'm good. All right. Almost done. Number 4. Holy moly, those are big numbers too. That reminds me I should probably check for a GCF. Well, what do you see? Okay, usually we start with our smallest number. Does 27 go into those numbers evenly? No, 27 times 2 is 54. That doesn't work. So I'm going to think of numbers that multiply to make 27. My first thought is 3 and 9. So we'll start with the bigger number. Does 9 go into 48 evenly? Bummer. Does not. Okay. Does 3 go into 48? It does. 3 times 16 makes 48. Okay. Does 3 go into 72? It does. And maybe you'd be using a calculator for this, but 3 times 24 makes 72. So then I have the 3 and the 9. So I do have a GCF of 3. And so just like we did before, I'm going to put that GCF out in front, and I'm going to divide everything by 3. That leaves me with a 16t squared plus 24t plus 9. I'm using what I put down here. If I divide by that 3, it just leaves me with those numbers left over. So I already did the work. Okay. All right, now I could just try to smiley face this, but maybe this is a shortcut. So my next question is, what about the first term? Is that first term perfect? Sure is. 4t is the square root of 16t squared. Okay, go to the last term. Is 9 perfect? You bet it is. Square root of 9 is 3. So then I go to the middle term again and I say, well, does 2 times each one of those give me my middle term? 2 times 4 is 8, times 3 is 24, and I have that t. So this is a perfect square trinomial. So I'm going to use my shortcut. The only difference is that 3 has to come along for the ride. So I'm still going to have, right, that 3 on the outside. Then I take the first term, which is 4t. I keep the sign that's first, which is the plus. And then I take that last term, which is 3, and I square it. So this right here is my answer. Okay, good. So the homework is going to be the worksheet 10.7, and basically you're going to be looking for, are they perfect squares? Are they perfect square trinomials? Are they difference of squares? Okay, we're going to look for both of those shortcuts. Okay? All right.